So the next one is drift speed. Drift speed of an electron. So we know metal contains a lot of free electrons, and if you take moment of one electron in a metal, so let us take one electron, let us take electron here, and electrons will be moving randomly in all directions. Let us pick up one electron here, that electron, assume that initially that electron is moving in this direction. Whenever it collides with a lattice point here, then there will be the direction of electron will the electron deviates from its path. The electron will move in this direction, let us say. Again it may have a collision here. Once it has a collision, the electron may come back in this direction. So this is how electron will be moving in all directions. Because of this reason, at any point maybe this electron is moving in that direction and some electron may be moving in opposite direction. So this is the reason why I said net flow of charge through any region in particular direction is zero. This is what happens in case of metal when there is no electric field. In the same case, if you apply electric field in this direction, then what happens? Then your electron will get drifted opposite to the electric field direction. So electron initially, if there is no electric field, it is going here and hitting there. Now electric field is there. Because of the influence of electric field, it cannot go there. It may go somewhere here and it may hit there. It may hit one more lattice point there. And again, after hitting here, so it may come in this direction and again it may hit there. It may hit once again with one lattice point. It may hit one lattice point there, and after here once again it hits the lattice point. It may come in this direction and it may reach here. So if there is no electric field, the electron is starting from here and coming here after 1-2 collisions, and when electric field is there, electron is coming somewhere here after the 2 collisions. So the electron is drifting because of the influence of electric field in this direction by this distance. So that is called drifting, right? Let us calculate what is the drifting speed here. So for that reason, let us compute what is the force acting on the electron. Let us take once again, let us take force acting on the electron. So the force acting on the electron will be equals to minus E, because E is electric field and small e is charge of an electron, that's negative. So that implies Ma equals to minus E. Then from here I can write A equals to minus E by M. This is what acceleration. This is what acceleration of the particle is. So when this is the acceleration of the particle, we know rate of change of velocity is defined as acceleration. So you can write down dv by dt equals to minus em by E by m. Then dv equals to minus E by m into dt. Right? So velocity of the electron here keep on increases until it has a collision. Once it has a collision, velocity becomes 0 once again and it starts again from there. So when you integrate this function, on both sides, so you get v minus v0 equals to minus E by m into t. Velocity of the electron increases with the time t. Velocity of an electron increases with the time t until it suffers a collision. Once it collides with the lattice point, and velocity becomes 0, and again it starts from the fresh. See here, from here to here there is an acceleration, and once it hits that, then its velocity becomes 0. Once again it will start accelerating. So again it hits here, and again velocity becomes 0. Once again it starts accelerating in this direction. So this is what. So v0 is here initial velocity. Initial velocity means immediately after the collision. Immediately after the collision, the velocity is highly random. So when you take average, let us compute average of these. Average. When you compute average of these, when you compute average of every parameter here and v0, because v0 is velocity of the electron immediately after collision. So that is a highly random. So you get 0. When you take average, you get 0. And this t is time period, time taken by the electron for the collision, and that is also not constant. So sometimes some collisions may happen in very short time, some collisions may happen in very long time. So this is also not a constant parameter, and it also alters. And v is that is what your drifting velocity is. So when you take average of every parameter here, average of every parameter here, and that will be v drifting, and that average will become 0 now, equals to minus E by m. And this is also not a constant parameter, and for collision to collision time period may change. So you get when you take average of that, you may get something that's, and this tau is called here relaxation time. Relaxation time. So you can also call it as time between two successive collisions. It's average time between two successive collisions, because time between two successive collisions is not constant. Time between two successive collisions may alter. So because of that, I am saying that this time, this is relaxation time, that is defined as average time between two successive collisions. So this is the velocity with which electron will be moving. That's called drift velocity. This is called drift speed or drift velocity. Drift velocity. This is drift velocity, and E is charge of an electron, and E is electric field, and m is mass of an electron, and there's a relaxation time. This is the relaxation time. Now in this case, let us consider once again, let us take one cylindrical conductor here. Say area of the cylinder is, let us say, A, and the length of the cylinder is also L. Length of the cylinder is L. Now I am applying electric field in this direction. Let us say I am applying electric field in that direction. Let us say if I apply electric field in this direction, then electrons will be drifting in this direction. Electrons will be drifting in that direction, and say this is same area A, and if you wait for delta t time, some electrons may cross this area. Is it right? If some electrons are crossing this area, so negative charges are crossing this area. So the effect will be same when same amount of positive charges are crossing this area in this direction. So because we define current as rate of flow of charge, rate of flow of positive charge, we will define current as rate of flow of positive charge. Positive charge. So if electrons are crossing this area in this direction, see, for let's say some number of charged particles are crossing in this area, some negative charges are crossing, the effect will be very similar when same amount of charge, same amount of positive charge is crossing this area in this direction, right? So now consider this situation. So this is the conductor, and now I am applying electric field in this direction. Say area of the cylinder is A, and length of the cylinder is L. So now if I apply electric field here, then electrons will be moving in this direction, then positive charges will be moving in that direction. Generally there are no positive movement of positive charge here, because metal has only free electrons, and free electrons can move. The positive lattice points cannot move. But the effect when electrons are going in this direction, the similar effect you will see when same amount of positive charge is going in this direction. So if electron is drifting in this direction with velocity Vd, so you can take similar effect when positive charges are drifting in that direction with the same velocity. So now all positive charges will be drifting in this direction with this velocity, with Vd velocity. If you wait for delta t time, so the electron which is starting from here, it can cover distance Vd delta t. Vd delta t. So it means that if you wait for delta t time, whatever electrons are there, here, whatever electrons are there in this region, they may cross this area. So the effect will be very similar when the same amount of positive charges are crossing this area. So if you compute here net flow of positive charge through this area in delta t time, so that will be, so let us write here, delta q equals to, delta q is amount of positive charge that is crossing this area in delta t time. So whatever electrons are there, whatever charged particles are there within this region will cross this area in delta t time, right? So then total amount of charge that goes through this area will be equals to total number of charged particles in this region times charge of individual. Now charge of an electron is minus E, then charge of positron will be positive charge will be plus E. So charge of each particle is E. Then how many charged particles are crossing? Let us compute that. How many charged particles will be in this region? That will be equals to number density times the volume of this cylinder. Then volume of this cylinder is, because A is area and V delta T is the length, so you get A V delta T, that is volume, and N is a total number of charged particles per unit volume. So this many particles, this many charged particles are there within this region, and the charge of each particle is E, right? So now this is amount of charge that is passing through this area in delta theta. So we know the current is rate of flow of charge, rate of flow of positive charge in this direction. So that equals to, from here you can write down NAVDE. So now I equals to NAVDE. This is what your I is. This is what your current is. I am taking the moment of positive charge. I don't take moment of negative charge, because by definition I will take current as a flow of positive charges, and here there is no positive charges. Here there is no flow of positive charges, only flow of negative charges is there, but the effect will be very similar when you but here in this case there is only flow of negative charges there. But if the same amount of, for example, if electrons are going in this direction, if let's say few electrons are going in this direction, the effect will be very similar when the same number of positive charges are going in that way. So because of that reason I am taking this step. So now I equals to NAVDE. So already we know VD is the drift to speed, and that we got from here. And here also I will take it as positive because I am taking the effect of positive charges. So now VD equals to, E by MT. This is relaxation time. So from these two equations, I can write down I equals to NAE, then VD is this part. So you can write ET by M. So that implies I equals to N E square and T E A by M. So then what is E here? E is electric field. If already I mentioned that length of the conductor is L and area is A. If electric field is E in between, then potential difference will be V. Maybe here it may be V and here it may be 0. Then V minus 0 equals to E by L, because electric field is defined as, so here you can write down, if V is the potential difference and electric field is E and length of the conductor is L, then here you can write down that E equals to V by L for this conductor. E is electric field and V is potential difference, L is length of the conductor, so you can write down this part here. Because electric field is defined as negative gradient of potential. When you take negative gradient, this is 0 minus V, already minus of minus V will be V, so that's what. So now I equals to N E square T, then E is V by L, so let us write down that is V by L. So N E square T, A is there, M is there, and instead of E I wrote V by L. Instead of E, I wrote V by L. That's all. So now let us rewrite this part. So I equals to, I am writing N E square T A by M into L into V. So V is voltage across, right? So you can also write down that as V equals to M L by N E square T A into I. So in this case, m is mass of the charged particle, electron, is constant, and L is length of the conductor, and A is area of the conductor, N is number of charged particle per unit volume, and E is charge of an electron, and T is relaxation time. And see, everything is constant. So that you can write down as V equals to R into I. That constant is resistance of the wire. That constant is resistance of the wire. Now let us write down the resistance of the wire here. The resistance of the wire equals to M by N E square T into L by A. And once again, if you see, the resistance depends on length of the conductor and area of the conductor. And M is mass of an electron, N is number density, and E square is E is a charge of an electron, and T is relaxation time. So this is a fixed for particular material. So for that reason, I am writing that as rho into L by A, and here rho is called specific resistance or resistivity. So rho is resistivity or specific resistance. So now this is a resistivity or a specific resistance. So now this is resistance, and resistance depends on properties of the material and dimensions of the material. But look at resistivity. The resistivity equals to M by N E square T. This does not depend on properties of, this does not depend on dimensions of the conductor, and it depends on, it's a fixed for particular material. For example, for particular material, there will be fixed number of N, because N is number of free electrons per unit volume. That may be different for different materials, and T is also different for different materials. And M is mass of an electron, that is same for every material, and E is charge of an electron, that is same for every material. So rho depends on the system, but resistance depends on the system plus dimensions of the body. So now this is the resistivity, and you can also define conductivity. Conductivity is defined as the reciprocal of resistivity. So you can write down E square T by M. And see here, conductivity depends on, once again let us see, conductivity depends on number of free electrons per unit volume and relaxation time, because E and M both are constant for any material. Now conductivity will be more when more number of free electrons are available, and also when relaxation time is very high, conductivity will be very high, and when relaxation time is very high, resistivity will be very low. When number of electrons per unit volume is very low, then resistivity will be very high, and so on. So this is what your conductivity and resistivity. And resistance equals to rho L by A. And you can also write down here conductance. Conductance equals to reciprocal of resistance. And the unit for resistance is ohm, or you can also write down like ohm. This is the symbol for ohm. And resistivity, the unit for resistivity is, see here, resistivity is ohm meter. This is the unit for resistivity. So this is the unit for resistance, right? So this is the, and somewhere I wrote, and see here, so V equals to Ri. So this is what your Ohm's law. Ohm's law says voltage across the conductor or the current in the conductor is proportional to voltage across the conductor. or you can write down current is proportional to voltage across the conductor. This is what Ohm's law is. This is what Ohm's law is. And you can write down that V is proportional to I and V equals to Ri, and R is resistance of the conductor. Resistance is the property of the material by which it opposes electric current through that.